All men are mortal. Socrates is a man, so Socrates is mortal. Any of us can see that this is correct, and yet the logic we built in part 1 cannot even write it down. Predicate logic can. Welcome to discrete mathematics. This is chapter 1, part 2, predicate logic. In part 1, we worked with whole statements that are simply true or false. That language cannot look inside a sentence. Predicate logic can. It talks about objects, about the properties they have, and about the words for all and there exists. Let's begin. This part has 3 common names. Predicate logic, first-order logic, often shortened to FOL, and the predicate calculus. They all mean the same thing. We study 5 things. First, the language of quantifiers. Those are the words for all and there exists. Second, logical equivalences, when 2 predicate statements always mean the same thing. Third, nested quantifiers, where one quantifier sits inside another. Fourth, translating from predicate logic into plain English. And fifth, translating from English back into predicate logic. Use this list as your checklist. Section 1.4, Predicates and Quantifiers. This is where we meet the 2 brand new ideas. Predicates, which describe properties of objects, and quantifiers, the words for all and there exists. This is the plan for the section. First, we meet predicates. A predicate is like a statement with a blank to fill in. Then variables, the letters that fill that blank. Then the 2 quantifiers, the universal one for all and the existential one there exists. After that, we learn how to negate a quantified statement, using De Morgan's laws for quantifiers. Then we practice translating English sentences into logic. And at the end, logic programming, which shows how these ideas power a real programming language called Prolog. Some correct reasoning simply cannot be written in propositional logic. A famous example shows why. We are told 2 facts. First, all men are mortal. Second, Socrates is a man. Does it follow that Socrates is mortal? Of course it does. Any person can see that. But watch what happens in propositional logic. Each sentence becomes just one letter, say P, Q, and R nothing connects them. Propositional logic cannot see that men in the first sentence is the same idea as a man in the second. The reasoning is invisible to it. To capture arguments like this, we need a language that can talk about individual objects, the properties they have, and the relations between them. Later in the chapter, we will prove this kind of argument step by step. Predicate logic keeps everything from propositional logic and adds 3 new tools. First, variables. We use letters like X, Y, and Z to stand for objects. Second, predicates. Written like P of X or M of X, a predicate, is a property that an object may or may not have. Third, quantifiers, which we will meet in a few slides. Put a variable and a predicate together, and you get a propositional function. For example, P of X, think of it as a proposition with a blank in it. Once you replace the variable with an actual object from its domain, it becomes a real statement that is true or false. A propositional function is not yet true or false because it has a blank in it. It becomes a real proposition with a definite truth value in one of 2 ways. Either we replace the variable with a value from the domain, or later, a quantifier binds it. We say that P of X is the value of the propositional function P at X. Let P of X mean X is greater than 0. The domain is the integers. We often write the domain with the capital letter U. Now fill in the blank. P of minus 3 asks, is minus 3 greater than 0? No, so it is false. P of 0 asks, is 0 greater than 0? No, still false. P of 3 asks, is 3 greater than 0? Yes, so it is true. A predicate can take several variables. Let R of x, y, z mean x plus y equals z, and let Q of x, y, z mean x minus y equals z. The domain is the integers for every variable. Look at R first. R of 2 minus 1, 5 asks, does 2 plus minus 1 equal 5? 2 plus minus 1 is 1, not 5, so it is false. R of 3, 4, 7 asks, does 3 plus 4 equal 7? Yes, so it is true. Now Q, the subtraction version. Q of 2 minus 1, 3. 2 minus minus 1 is 3, so true. Q of 3, 4, 7. 3 minus 4 is minus 1, not 7, so false. Same two predicates, same integer domain, but this time we fill only one slot. Look at R of x, 3, z we fixed y to 3, but x and z are still blank, so it is not a proposition at all. It has no truth value. The same happens with Q of x, 3, z here y is 3, but x and z are still free, so again it is not a proposition. The lesson: leave any variable unfilled, and you do not yet have a statement. You only get a truth value once every blank is filled. The connectives we learned in propositional logic, not, and, or, and the if-then arrow, all work in predicate logic too. Let P of x mean x is greater than 0. P of 3 or P of minus 1 is true or false, and or needs just one true part, so the whole thing is true. P of 3 and P of minus 1 is true and false, and it needs both, so it is false. P of 3 arrow P of minus 1 is true arrow false. An arrow is false only when it goes from true to false, so this is false. P of 3 arrow not P of minus 1 is true arrow not false, which is true arrow true, so it is true. But be careful. As soon as an expression still holds a free variable, like P of 3 and P of y, it is not a proposition and has no truth value. The fix comes next. Quantifiers bind those variables and turn these expressions into real propositions. Now we meet the tools that make predicate logic powerful, quantifiers. We need them for English words like all and some. All men are mortal talks about every man. Some cats do not have fur talks about at least one cat. There are two main quantifiers. The universal quantifier reads for all, and we write it as an upside-down capital A. The existential quantifier reads there exists, and we write it as a backwards capital E. The portrait is Charles Peirce, a logician who did early work on quantifiers. Now how do we write them down? A quantifier goes in front of the variable. For all x, P of x asserts that P of x is true for every single x in the domain. There exists x. P of x asserts that P of x is true for at least one x in the domain. Once a quantifier is attached, we say it binds the variable x. And that is the important part. A bound expression is no longer a blank waiting to be filled. It is a real proposition with a truth value. This is the universal quantifier. We write it with an upside-down capital A in front of x, followed by P of x. We read it out loud as for all x. P of x, it says that the property P is true for every single object in the domain. Let P of x mean x is greater than 0, and let the domain be all the integers. Is it true for every integer? No, because 0 is an integer and 0 is not greater than 0. so it is false. Same property, but now the domain is only the positive integers. Every positive integer is greater than 0, so now it is true. And x is even over all the integers is false, because 3 is an integer and 3 is not even. This is the existential quantifier. We write it with a backwards capital E in front of x, followed by p of x. We read it as there exists x, p of x, or for at least one x, p of x. It says the property p is true for at least one object in the domain. Look at the examples. X is greater than 0 over the integers is true, because 3 is greater than 0. It is still true over the positive integers. But x is less than 0 over the positive integers is false, because no positive integer is less than 0. And x is even over the integers is true, because 2 is even. Now 2 rules worth memorizing. They are opposites of each other. To break a for all statement, you only need one counterexample, just one object where the property fails. Look back at x is greater than 0 over all the integers. 0 alone already makes it false. To prove a there exists statement, you only need one witness, just one object that works. For x is greater than 0 over the integers, 3 is enough. One counterexample destroys a for all. One witness establishes a there exists. A helpful way to picture quantifiers. When the domain has only finitely many objects, think of quantification as a loop that walks through them one by one. For all x, p of x, loop through every object. If the property is true at every step, the whole statement is true. But as soon as you hit one object where the property is false, you can stop right away and declare the whole statement false. For there exists x, p of x, loop again. As soon as you find one object where the property is true, you can stop and declare the whole statement true. If you reach the end of the loop and never found one, then the statement is false. So remember, for all is a loop looking for the first failure, and there exists is a loop looking for the first success. One warning: if the domain is infinite, you can still imagine the loop, but it might run forever. So this is only a mental picture, not a real method of computation. This slide drives home one point. The answer changes when you change the domain, even if the predicate stays the same. Let's read the table row by row. First row, over the positive integers with p of x being x is less than 2. There exists such an x because 1 is less than 2, so the existential is true. But not every positive integer is less than 2, since 3 is not, so the universal is false. Second row, over the negative integers with the same x less than 2. Every negative integer is less than 2, so both the existential and the universal are true. Third row, the domain is just the set 3, 4, 5, and p of x is x greater than 2. All three are greater than 2, so both are true. Fourth row, same little domain, but now x less than 2. None of 3, 4, 5 is less than 2, so both are false. Same symbols, but the domain decides the truth. This slide is about a bracketing rule. The quantifiers for all and there exists bind more tightly than any of the connectives like and, or, and the arrow. A quantifier reaches out and grabs only the smallest piece right next to it. Look at the first line. When you write for all x, p of x, or q of x, the for all only binds the p of x part. So it really means, in brackets, for all xp of x, close bracket, or q of x. Notice that the q of x on the end is outside the reach of the quantifier. If you actually want the quantifier to cover the whole P or Q, you must add parentheses around P of X or Q of X. Unfortunately, many people write the first form when they mean the second. The safe habit is to always add parentheses and say exactly what you mean. Now we translate an English sentence into predicate logic. Every student in this class has taken a course in Java. Step 1. Find the unknowns. The property the sentence talks about is taking a Java course, so let J of X mean X has taken a course in Java. Step 2. Read the quantifier word. The word is every, so we need the universal quantifier for all X. Step 3. Now choose the domain. Take the domain to be the students in this class. Then every X is already a student, so we need nothing more. The answer is, for all X, J of X. Step 4. Try a bigger domain, all people. Now the domain holds people who are not in this class, so we need a second predicate. Let S of X mean X is a student in this class. Step 5. Guard the claim with an if-then. For every person, if that person is a student in this class, then that person has taken Java. That is, for all X, S of X arrow J of X. Watch the common mistake at the bottom. Writing for all X, S of X and J of X is wrong. It would say every person in the world is a student here and has taken Java. With a for all, the glue is the arrow, not the end. This is the same task, but with some instead of every. Some student in this class has taken a course in Java. Step 1. The property is the same one, so keep J of X for X has taken a course in Java. Step 2. Read the quantifier word. The word is some, so we need the existential quantifier, there exists X. Step 3. Take the domain to be the student in this class. Then the answer is short, there exists X, J of X. Step 4. Now take the domain to be all people. As before, we need S of X for X is a student in this class. Step 5. We want one person who is a student here and who has taken Java. Both facts must hold for the same person, so we join them with and. The answer is, there exists X, S of X and J of X. Watch the mistake at the bottom. Writing there exists X if S of X then J of X is wrong. An arrow with a false first part is automatically true, so one person outside this class already makes it true. Remember the pairing. For all goes with the arrow, and there exists goes with the end. Remember the Socrates argument from the start of this chapter, the one that plain propositional logic could not handle. Now we can write it properly. The domain is all people. Step 1. Find the unknowns. Two properties appear in the argument. Man of X means X is a man. Mortal of X means X is mortal. Step 2. Translate the first premise. All men are mortal uses the word all, so it is a for all with an arrow. For all X, if man of X, then mortal of X. Step 3. Translate the second premise. Socrates is one named person, not a whole group, so there is no quantifier at all. We simply write man of Socrates. Step 4. The conclusion uses the other predicate at that same person, mortal of Socrates. Propositional logic could not reach inside the sentences to see this shared structure, but predicate logic can. Later, when we study rules of inference, we will formally prove that the conclusion really does follow. This slide says what it means for two quantified statements to be equivalent. Two statements with predicates and quantifiers are logically equivalent when they always have the same truth value. And always is demanding here. It must hold for every predicate you plug in. and for every domain of discourse, you choose for the variables. When two statements S and T are equivalent, we write S, then a triple bar sign, then T. Now let's work an example. Show that for all x, not S of x is equivalent to for all x, S of x. Line 0 is the statement we start with. For all x, not S of x. Step 1. The double negation not cancels. Saying it is not the case that S of x is not true is just saying S of x is true. So the line becomes for all x, S of x, that is the right-hand side, so the two are equivalent. The important thing to remember is that equivalence is a strong claim. Checking one predicate or one domain is not enough. It must agree for every predicate and every domain at the same time. A useful way to picture quantifiers. Suppose the domain is finite, that is, it has only a few elements. Then a quantifier is just a chain of connectives. A for all statement is really just an and of all the cases. And a there exists statement is really just an or of all the cases. One warning before we try it. If the domain is infinite, this idea still helps you think, but the chain of connectives would go on forever. So we keep the short quantifier symbol instead. Let's try it on a real domain. Let the domain be the integers 1, 2, and 3. Then for all x, p of x is the same as p of 1 and p of 2 and p of 3. And there exists x, p of x is the same as p of 1 or p of 2 or p of 3. Look at what each one demands. The unchain needs all three to be true. The or chain needs at least one to be true. That is exactly the difference between for all and there exists, written out in full. Now we learn how to negate a quantified statement. Start with for all x, j of x, where j of x means x has taken a Java course, and the domain is the students in your class. In words, this says every student has taken Java. What does it mean to deny this? It means it is not the case that every student has taken Java. Think carefully. To break the claim that everyone did it, you only need one person who did not. So the negation says there is a student who has not taken Java. Symbolically, not for all x, j of x is equivalent to there exists x such that not j of x, the negation of every x turns into some x that fails. This is the reverse of the last slide. Start with there exists x, j of x, which says some student in the class has taken Java. What does it mean to deny this? It means it is not the case that any student has taken Java. If not even one student took it, then every single student did not take it. So the negation says, for all x, not j of x. Symbolically, not there exists x, j of x is equivalent to for all x, not j of x. Notice the pattern. The quantifier flips and the not moves inside next to the predicate. Now we collect both rules into one named result, De Morgan's laws for quantifiers. Take the first law. Line 0 is not for all x, p of x. Move the not inward. The for all flips to there exists and the not lands on the predicate. We get there exists x, not p of x. Now the second law. Line 0 is not there exists x, p of x. Move the not inward again. This time there exists flips to for all. We get for all x, not p of x. And this is the recipe to memorize. To move a not sign past a quantifier, flip the quantifier and put the not against the predicate inside. You will use this again and again, especially with nested quantifiers. Now let's read each law as a claim about the domain. The first row, not there exists x, p of x, is the same as for all x, not p of x. This negation is true when p of x is false. For every x it is false as soon as there is one x, making p of x true. The second row, not for all x, p of x, is the same as there exists x, not p of x. This negation is true when there is at least one x, making p of x false. It is false only when p of x holds for every single x. Let's translate an English sentence into logic. Some student in this class has visited Mexico. The domain is all people, not only students, so we will need two predicates. Step 1. Find the unknowns. The first property is being a student here. Let S of x mean x is a student in this class. Step 2. The second property is visiting Mexico. Let M of x mean x has visited Mexico. Step 3. Read the quantifier word. The word is some, so we use there exists x. Step 4. The domain holds people who are not students here, so the same person must be a student and must have visited Mexico. Join the two facts with and. Step 5. Put the quantifier in front. The answer is, there exists x, s of x, and m of x. Now the second sentence. Every student in this class has visited Canada or Mexico. We keep the same domain and the same two predicates. Step 1. Find the missing unknown. Visiting Canada is new, so let C of x mean x has visited Canada. Step 2. The words Canada or Mexico are joined by or. That is a disjunction, m of x or c of x. Step 3. The claim is only about students, so we guard it with an arrow. If s of x, then m of x or c of x. Step 4. The word every is the universal quantifier. Put for all x in front. The answer is, for all x, s of x arrow in parentheses, m of x or c of x. Notice the pattern in the box. With the domain all people, some student uses there exists with and, but every student uses for all with the arrow. Now some fun practice with silly words so you focus on the logic and not the meaning. Our universe U holds every object that is a fleegle, a snurd, or a thingamabob. One object may well be a fleegle and a snurd at the same time. F of x means x is a fleegle. S of x means x is a snurd. T of x means x is a thingamabob. We keep this same setup for the next several slides. First task, translate everything as a fleegle. Step 1, read the quantifier word. Everything is the universal quantifier for all x. Step 2, find the property being claimed. It is being a fleegle, which is f of x. Step 3, put the two parts together. For all x, f of x in words, every object in the universe is a fleegle. Same fleegle universe as before. Now translate nothing is a snurd. Step 1, read the quantifier word. Nothing says no such object exists, so we start with a not in front of there exists. Step 2, the property is being a snurd, which is s of x. Step 3, put them together. Not there exists x, s of x. Now we push the negation inward. Line 0 is, not there exists x, s of x. Apply the De Morgan law for quantifiers. There exists flips to for all and the not lands on the predicate. We get, for all x, not s of x. In plain words, saying nothing is a snurd is the same as saying every single thing is not a snurd. Both describe the same empty situation. Same universe. Translate all fleegles are snurds. Step 1. Read the quantifier word. All is the universal quantifier for all x. Step 2. Be careful here. The sentence does not say everything is a fleegle. Being a fleegle is the condition, the if part. So we write f of x arrow something. Step 3. What is the something? It is being a snurd. So the arrow points to s of x. Step 4. Put the quantifier in front. For all x, f of x arrow s of x. Remember this pattern well. All a or b always becomes for all x. A of x arrow b of x. The universal quantifier pairs with the if-then arrow. Same universe. Translate some fleegles or thingamabobs. Step 1. Read the quantifier word. Some is the existential quantifier, there exists x. Step 2. What must that object be? First, a fleegle, that is f of x. Step 3. The same object must also be a thingamabob at the same time. Two facts about one object are joined with and, so we get f of x and t of x. Step 4. Put the quantifier in front. There exists x, f of x, and t of x. Compare this with the last slide. All a or b used for all with the arrow, but some a or b uses there exists with and. Keep the two patterns clearly apart. Same universe. Translate no snurd is a thingamabob. Step 1. The word no says no such object exists, so we start with a not in front of there exists. Step 2. What would such an object be? A snurd and a thingamabob at the same time. That is s of x and t of x. Step 3. Put them together. Not there exists x, s of x, and t of x. Now we simplify that statement, one step at a time. Line 0 is the statement we just built. Not there exists x, s of x, and t of x. First step. Apply De Morgan for quantifiers. There exists flips to for all and the not moves inside. We get for all x, not in parentheses, s of x and t of x. Second step. Apply the ordinary De Morgan law on the end. Not of a and b becomes not a or not b we get for all x, not s of x or not t of x. In words, every object is either not a snurd or not a thingamabob. No object is both. Last one in the Fleegle world. Translate. If any fleegle is a snurd, then it is also a thingamabob. Step 1. Watch the word any. Here it means every, so this is the universal quantifier for all x and not there exists. Step 2. Look at the if part. It says x is a fleegle and x is a snurd. Two conditions on one object, so we bundle them with and f of x and s of x. Step 3. The then part is the third property being a thingamabob. That is t of x. Step 4. Join the two halves with the arrow and put the quantifier in front. For all x in parentheses f of x and s of x, close, arrow t of x. This is a small but common trap. The English word any often means for all, especially at the front of an if clause. Predicate logic is not only for pure mathematics. Engineers use it to write down, in an exact way, the rules that a computer system must obey. Rule 1. Every mail message that is bigger than 1 megabyte will be compressed. Rule 2. If a user is active, then at least one network link will be available. To turn these English sentences into logic, we first pick our predicates. L of m and y means mail message m is larger than y megabytes. C of m means message m will be compressed. Of u means user u is active. And S of n and x means network link n is in state x on the next slide. We put these together with quantifiers. Now we assemble the first rule. Every mail message larger than 1 megabyte will be compressed. Step 1. Find the unknown. The sentence talks about mail messages, so our variable m ranges over mail messages. Step 2. Larger than 1 megabyte is our predicate L, with the size set to 1. That is L of m and 1. Step 3. Then the message will be compressed. That is C of m. Step 4. The words every message that is larger will be compressed give a for all with an arrow. So we write, for all m, L of m and 1 arrow C of m. Now the second rule. If a user is active, at least one network link will be available. Step 1. Read the if part. If a user is active means there is some user who is active, so we write there exists u, A of u. Step 2. Read the then part. At least one network link is again a there exists, this time over links, there exists n. Step 3. The word available is the state, the second slot of S, so we write S of n and available. Step 4. The two halves are joined by if then, so we use the arrow. The whole rule is, there exists u, A of u, arrow, there exists n, S of n and available. This is how a specification document can be made precise enough to check against. This famous puzzle comes from Lewis Carroll, the author of Alice in Wonderland. His real name was Charles Lutwidge Dodgson, and he was also a logician. An argument is made of premises and a conclusion. The premises are the statements we are given. The conclusion is what we hope follows from them. The first premise, all lions are fierce. The second premise, some lions do not drink coffee. And the conclusion, some fierce creatures do not drink coffee. Does this conclusion really follow? It feels right, but feelings are not proof. To reason about it carefully, we first translate each sentence into predicate logic, which we do next. Now we translate the argument. Step 1. Find the unknowns. 3 properties appear. The first is being a lion, so P of X means X is a lion. Step 2. The second is being fierce. Q of X means X is fierce. Step 3. The third is drinking coffee. R of X means X drinks coffee. Step 4. Translate the first premise. All lions are fierce uses the word all, so it is a for all with an arrow. For all X, P of X arrow Q of X. Step 5. Translate the second premise. Some lions do not drink coffee uses the word some, so it is a there exists with an and. There exists X, P of X, and not R of X. Step 6. The conclusion has the same shape but about fierce creatures. There exists X, Q of X, and not R of X. Watch the pattern. The word all pairs with for all and an arrow. The word some pairs with there exists and an and. Mixing these up is the most common translation mistake. These 3 words are worth knowing. An assertion is valid if it is true no matter what, for every possible domain, and every meaning we give its predicates. An assertion is satisfiable if it is true in at least one case, some domain and some meanings. And an assertion is unsatisfiable if it can never be true. The first example is valid. For all X, not S of X is logically the same as not there exists X, S of X, and that holds for any S. The second example, for all X, F of X if and only if T of X is not always true, but we can certainly make it true, so it is satisfiable. The third example says for all X, F of X and not F of X nothing can be both F and not F at the same time, so this can never hold. It is unsatisfiable. Now the scope of a quantifier. The scope is simply how far the quantifier reaches, which part of the formula its variable controls. In the first example, for all x, f of x or s of x, the for all x reaches over the whole parenthesis. So we say x has wide scope. In the second example, for all x, f of x, closed off, or for all y, s of y here the first for all x only reaches its own small parenthesis around f of x, so x has narrow scope. Knowing the scope tells you exactly which occurrences of a variable a quantifier is talking about. Predicate logic is not just theory. It powers a real programming language called Prolog. The name comes from programming and logic. It was built in the 1970s by researchers in artificial intelligence. A Prolog program is made of two things: facts and rules. Look at the facts. Each line states one true thing. Instructor of Chan and Math 273 says Professor Chan teaches the course Math 273. Enrolled of Kevin and Math 273 says the student Kevin is enrolled in Math 273. So instructor of P and C means Professor P is the instructor of course C, and enrolled of S and C means student S is enrolled in course C. These facts are just predicates known to be true. Facts alone are limited. Rules let Prolog derive new information. First, a convention. In Prolog, a name that starts with a capital letter is a variable, like a blank to be filled in. Suppose teaches of P and S means Professor P teaches student S. We can write the rule. Teaches of capital P and capital S if instructor of P and C and enrolled of S and C. The turnstile symbol :dash means if, the comma means and. In plain logic, this rule says, for all P, for all C, for all S, if Professor P is the instructor of course C and student S is enrolled in course C, then P teaches S, so a professor teaches any student who sits in a course they instruct. Once the facts and rules are loaded into the Prolog interpreter, we can ask it questions, called queries. The question mark is the prompt the interpreter shows when it is ready. We ask, is Kevin enrolled in Math 273? We type question mark, enrolled of Kevin in Math 273. Prolog looks in its program, finds that exact fact, and answers yes. So a query with only constant names is a simple true or false question, and the answer here is yes. Queries become powerful when we use variables. Remember, a capital letter is a variable, a blank to be filled. Ask enrolled of capital X in Math 273. Who is enrolled in Math 273? Prolog searches for values of X that make this true. It finds X equals Kevin and returns it. You type a semicolon to ask for another answer. Prolog finds X equals Kiko, then a semicolon again, and this time it answers no, meaning there are no more. The interpreter is searching for an instantiation of X, one value at a time. The second query, teaches of X in Juana, asks which professors teach Juana. The answers are Patel and Grossman. Notice teaches was never stated as a fact. Prolog works it out using the rule from the previous slide, combining instructor facts with enrolled facts. One more query. We ask teaches of Chan and capital X, which students does Professor Chan teach? Chan instructs Math 273, and Kevin and Kiko are enrolled in Math 273. So Prolog derives X equals Kevin and X equals Kiko, then answers no when there are no more. If you would like to learn Prolog properly, there is a free online book called Learn Prolog Now at learnprologno.org. This was only a small taste. Logic programming is a whole field, and it grows directly out of the predicate logic we have been studying. Section 1.5. Nested Quantifiers. So far each statement used a single quantifier. Many real ideas in mathematics and computer science need one quantifier inside another. For example, for every number there exists a bigger number. Until now, we used one quantifier at a time. Now we put one quantifier inside another. This is the plan for the section. First, we meet nested quantifiers and see why we need them. Then the most important idea of the section. The order of the quantifiers matters. For all x, there exists y can mean something completely different from there exists y for all x. After that, we practice turning nested quantifiers into plain English. Then translating mathematical sentences into logic. Then translating English sentences into logic. And finally, negating a nested quantifier. Take your time with the order part. It is where most mistakes happen. Nested quantifiers let us say rich things. They express many English sentences and many important ideas in computer science and mathematics. Take this one. Every real number has an additive inverse. Step 1. Fix the domain. Both x and y range over the real numbers. Step 2. Read the outer quantifier. Every real number is for all x. Step 3. Read the inner part. Has an additive inverse means there is some number y that adds with x to give 0. That is, there exists y, x plus y equals 0. Step 4. Put the two quantifiers in order. For all x, there exists y, x plus y equals 0. Whatever number x you pick, you can find a partner y, its negative that adds up to 0. One helpful picture. Peel the statement like an onion. The whole thing is for all x. Of q of x, the inner part q of x is itself quantified. There exists y, p of x and y, and the innermost part is the plain equation x plus y equals 0. When the domain is finite, you can imagine checking a nested quantifier with two loops, one inside the other. Look at the left side, testing for all x. For all y, p of x, y the outer loop walks through every x for each x. The inner loop walks through every y if you ever find a single pair that makes p false. You can stop right away. The whole statement is false. Only if every pair passes is the statement true. Now the right side, testing for all x. There exists y. P of x, y again, the outer loop walks through every x, but now, for each x, the inner loop is hunting for just one good y that makes p true, and it stops the moment it finds one. If some x has no good y at all, the whole statement is false. If every x finds its partner, the statement is true. One warning. If the domain is infinite, the loop may run forever, but the mental picture still shows you the meaning. Now the heart of the section. Does the order of the quantifiers matter? Sometimes no. Take p of xy meaning x plus y equals y plus x because addition can be done in either order. For all x for all y, and for all y for all x say the very same thing, and both are true. When two quantifiers are of the same kind, the order does not matter. But now the important case. Take q of xy meaning x plus y equals 0. Read, for all x there exists y, x plus y equals 0. For each x we pick y to be its negative and it works. This is true. Now swap them. There exists y for all x, x plus y equals 0. This claims one single y works for every x at once. No such y exists. This is false. The difference is who chooses second. In for all x there exists y, each x picks its own y and there exists y. For all x, one y must serve all x when you mix the two quantifiers. Swapping them can change true into false. Let's practice. The domain is all real numbers, and p of xy says x times y equals 0. Check all four orders. First, for all x, for all y that would need every product to be 0, but 2 times 3 is 6, not 0. So this is false. Second, for all x, there exists y for any x, choose y equals 0. Then x times 0 is 0. It always works, so this is true. Third, there exists x, for all y choose x equals 0. Then 0 times any y is 0. So 1x works for all y true. Fourth, there exists x. There exists y, just take x0 and y0. True. Notice only the first case failed. Same idea, new predicate. Now x is any real number, and y is any real number except 0, so the division always makes sense. P of xy says x divided by y equals 1. First, for all x, for all y 4 divided by 2 is 2, not 1, so false. Second, for all x, there exists y, this fails already at x equals 0. 0 divided by any non-zero y is 0, never 1, so false. Third, there exists x, for all y no single x can give quotient 1 for every y at once, since changing y changes the quotient. False. Fourth, there exists x. There exists y, just take x equals 1 and y equals 1. 1 divided by 1 is 1. True. So only the exists case works here. Compare with the previous slide. The same four orders gave very different answers. This table is a reference card for every way to quantify two variables. Let's read it row by row. Top row, for all x for all y. True when p holds for every single pair, and false the moment one pair fails. Because both are for all, the order does not matter. Second row, for all x, there exists y. True when every x can find at least one partner y that works, and false when some x has no partner at all. Third row, there exists x for all y. True when one special x makes p true against every y, and false when for each x you can find some y that breaks it. Rows 2 and 3 look similar, but they are not the same, because the order is swapped. Bottom row, there exists x, there exists y. True when at least one good pair exists anywhere, and false only when p fails for every pair. Since both are there exists, the order does not matter here either. Now we turn logic back into English. Read the formula one piece at a time. C of x means x has a computer. F of xy means x and y are friends. The domain is all students in your school. Step 1. The outermost part is for all x, so we take every student x, one at a time. Step 2. The first thing inside is C of x, that says this student has a computer. Step 3. The second thing inside is there exists y, C of y and F of xy, that says some student y has a computer and is a friend of x. Step 4. The two pieces are joined by or, so at least one of them must hold. Put it together in plain English. Every student in your school has a computer, or has a friend who has a computer. This one is trickier, so read it slowly piece by piece. F of xy still means x and y are friends. Step 1. The outermost part is there exists x, so there is at least one student x. Step 2. Next come two universal quantifiers, for all y, and for all z, so we take any two students y and z. Step 3. The if part says f of xy and f of xz, and y is not equal to z, that means both y and z are friends of x, and they are two different people. Step 4. The then part is not f of yz, so those two friends are not friends with each other. Put it together. There is a student none of whose friends are also friends with one another. Many math sentences hide their quantifiers, and our job is to bring them into the open. Translate. The sum of two positive integers is always positive. Step 1. Rewrite the sentence so the for every and the if are visible. For every two integers, if both are positive, then their sum is positive. Step 2. Find the unknowns. Give the two numbers names x and y and fix the domain as all integers. Step 3. Write the condition. Both numbers are positive, x greater than 0 and y greater than 0. Step 4. Write the claim. Their sum is positive, x plus y greater than 0. Step 5. Join the condition and the claim with an arrow and put both quantifiers in front. For all x, for all y, x greater than 0 and y greater than 0, arrow, x plus y greater than 0. Notice the trick. Instead of restricting the domain to positive integers, we keep all integers and put the positivity in the if part. Now we go from English into logic with 3 different domains. Translate. There is a woman who has taken a flight on every airline in the world. Step 1. Find the unknowns. The first relation is a woman taking a flight. P of W and F means W has taken flight F, where W ranges over all women and F over all flights. Step 2. The second relation links a flight to an airline. Q of F and a means F is a flight on airline A, where a ranges over all airlines. Those two predicates are all the vocabulary we need. We keep the same two predicates and now build the quantifier prefix, left to right. Step 3. There is a woman gives there exists W. Step 4. On every airline gives for all A. Step 5. Has taken a flight on that airline gives there exists F, with the inside saying she has taken that flight, and that flight is on that airline. Step 6. Read the prefix left to right. There exists W, for all I there exists F, P of W F and Q of F, A. The order of the quantifiers is the whole meaning here, so read it slowly. 6 quick translations. In each one, pick the obvious predicate and write the logic. 1. Brothers are siblings. If X is a brother of Y, then X is a sibling of Y for all X, for all Y, B of XY arrow S of XY. 2. Siblinghood is symmetric. For all X, for all Y, S of XY arrow S of YX. 3. Everybody loves somebody. For all X, there exists Y, L of XY. 4. There is someone who is loved by everyone. There exists Y, for all X, L of XY. 5. There is someone who loves someone. There exists X, there exists Y, L of XY. 6. Everyone loves himself. For all X, L of XX, with the same variable in both slots. Now compare 3 and 4 carefully, because they look almost the same. 3 is everybody loves somebody. For all X, there exists Y, L of XY. Each person may love a different person. Your someone need not be my someone. 4 is there is someone who is loved by everyone. There exists Y, for all X, L of XY. Now one single person must be loved by everybody. That is a much stronger claim. Swapping the order of for all, and there exists completely changes what the sentence says. Now we negate a statement with 3 quantifiers. Recall the airline statement. There exists W for all A, there exists F, P, and Q. Express this. There does not exist a woman who has taken a flight on every airline. Step 1. The hard work of naming the predicates is already done. so we start from the airline statement. Step 2. Read the new sentence. There does not exist a woman who, and so on, denies the whole statement, not just one part of it, so the not goes in front of everything. Step 3. Write it down. Not there exists W, for all there exists F, P of WF and Q of FA that answers the first part. On the next slide, we do the real work. We push that not inward, one quantifier at a time. Line 0 is the statement we ended with the not in front of the whole thing. Step 1. The not meets there exists, W not there exists becomes for all, so we get for all W not and the rest follows. Step 2. Now the not meets for all A not for all becomes there exists. We get for all W, there exists a not and the rest. Step 3. Now the not meets there exists F again, it flips to for all. We get for all W, there exists a for all F not in front of the parentheses. Step 4. The not now sits in front of P and Q. Use the ordinary De Morgan law. Not P and Q becomes not P or not Q, the final line is. For all W, there exists a for all F, not P of WF, or not Q of FA. Read it back in English. For every woman there is an airline such that, for all flights, she has not taken that flight, or that flight is not on this airline.